Yes, welcome back. So, as anticipated before lunch, or before the break, we will continue now with the section 3 on planning and development. And our speaker is Markus Drapalik from the University of Natural Resources and Life Sciences in Vienna. He has a background as a physicist, and he has worked 15 years in renewable energies, 10 of which in wind. And on top of that, he is an active user of a small wind turbine with Piggott. He will maybe also mention that. So, Markus, I can see the screen. Can you?
So now you can hear me.
Yes.
Great.
Welcome.
Thank you very much, and thank you for having me. Actually, this is a work of my colleague Larissa and me, and probably she would have been more qualified to talk about it, but she couldn't make it. So yeah, you have to make do with me. Yeah, you already mentioned my background. I have been working with large and small wind turbines alike, and I have a little focus on ice throw risks. But yeah, what might be interesting to you is the institute I'm working at, which is the Institute of Safety and Risk Sciences of the University of Natural Resources and Life Sciences in Vienna. And we have here an interdisciplinary team with quite a large range of topics, from nuclear to renewables, biotechnology, advanced materials, and so on. And one overarching theme of the institute is a prospective technology assessment, which means we try to analyze a technology, preferably at an early stage, and of course find the risks, the probabilities, the shaping possibilities. And in this, we want to identify sensitive points in the technology, and that way find out how to improve it, and at the same time avoid this kind of lock-in effects where you have established some kind of technology and with its problems and can't get out of it anymore. Yeah, so we're starting with this background. We thought about what can we do for small wind turbines, and so I thought I start to think about why even have them, and yeah, if I asked you why are you interested in small wind turbines, I mean, don't worry, I won't ask you because I teach at the university and I don't expect people to answer if I ask them something. Yeah, probably it won't be for the low cost, because that's also why I asked in the beginning what's the cost of energy. It's of course depending on the site and so on. It's compared to, for example, photovoltaics is relatively high, so that's really not so much of a motivation to build a small wind turbine. I know it's different for medium-sized turbines. Then you have the maintenance, which is necessary, and it should be done by qualified personnel and so on. And so that's also not so comfortable compared with PV, which you just put there and usually works a long time without much maintenance. And then we have, in the context of urban use, the problem that building integration is really challenging. You have the vibration problems and, of course, licensing and so on issues. So yeah, that's probably not why I would go towards small wind. Then of course you have off-grid, and off-grid application that's always interesting, especially in a mix with PV. Then, of course, we have the very strong reason of making a statement, which can sometimes go towards greenwashing. I mean, I have the giraffe here. I don't want to associate the giraffe with greenwashing. That's not what I mean here. That's for making a statement, right? But yeah. And finally, I think what's really a driving force for many of us is that we want to have a way of having renewable, eco-friendly energy. And with this in mind, we of course have to ask ourselves, well, how carbon neutral is wind energy really? And if we look at large wind turbines, we see here, of course, it's quite carbon neutral and better than most alternatives. But of course, there is still a residual amount of CO2 per kilowatt, which is released. And that's for large wind turbines. And when I went into literature, I saw that there isn't much published on small wind turbines. So we don't know much about how actually eco-friendly they are, or how sustainable they are. And the few studies you find give a very wide range of values there. So we thought we have to look into this ourselves. And so what we wanted to know is basically the energy payback time. We wanted to look into the global warming potential, identify the biggest contributors in the system of a wind turbine, and identify the improvement potential. And for this, we took two very different turbines and analyzed them. One is a Schaffner 05, so it's a 5 kilowatt turbine, roughly 6 meter diameter, mostly made from concrete, steel, and GFRP. And we have a Piggott turbine, so it's a self-made turbine. As mentioned, we own one, so a small 400 watt turbine. Actually, we rated the generator at 600 watt, but we didn't ever get more than 400 out of it. So let's say 400 watt turbine with 1.2 meters diameter and mostly steel and wood. And from a methodological perspective, how did we look at it? Well, we choose to make a life cycle assessment. What does this mean? Well, the basic idea of an LCA, for those of you who maybe don't know this too well, is to describe the whole life of a product as a series of individual processes, each of which transforms some input into an output, and inputs are usually some kind of resources and energy, and output is again some kind of energy, some resources, and of course emissions. So emissions is what you can't use anymore and is actually lost into the environment. And you see here on the left that what is included is the use of raw materials, the transport, manufacturing, distribution, end of life. And what we didn't include here is recycling. So this is cradle to grave analysis, not cradle to cradle. Okay. We used OpenLCA, an open source software for doing LCA analysis. We used the EcoInvent database as input for the resources, and we did the final impact assessment using recipe 2016 and also added the energy demand. And recipe 2016 defines which indicators are tracked throughout the LCA, and there are several ways on how you can assess them in detail. In fact, it doesn't matter that much for us here, because this is mostly focused on seeing which part of the turbine are more or less important, and this doesn't change too much with the different possibilities you have there. So in the end, we had 19 indicators. They are listed here for reference. Yeah, and the object of our interest is one wind turbine, of course, which we divided in 3 subsystems. One being the actual turbine, so the rotor, hub, generator, cabling there. Then we have tower and foundation, and the electrical system. So with these subunits, we can define our system boundaries. And yeah, so what were the main processes here? We have the resource depletion mining, which goes into the manufacturing of the primary materials, which again go into manufacturing of our 3 subsystems: turbine, tower, and electrical system. Then we have the installation, operation, deconstruction, and of course the end-of-life treatment. And in between any of these processes, we have some transport processes. Depending on the turbine, they are quite different, of course. Yeah. So to analyze these systems over the whole lifetime, of course, we need to know what these, we need to know the performance of the turbines. So we had them at 2 different sites. The Schaffner 05 was at the test facility in Lichtenegg, which is a more or less rural location, hilly with rather high turbulence. The average wind speed was around 5 meters per second at installation height. And we had 1 year of measurements for the performance. And in that case, the Schaffner 05 is grid connected, and we had rather coarse production data. And the Piggott turbine is at the site of the university, which is yeah, a suburban site, quite low wind speed, also because the tower was rather low, so below 10 meters, and also 1 year of measurements. And this is a battery system, so it's an isolated operation. And yeah, since this is an experimental installation, we had high resolution data. Okay, and what did we get out of it? So let's look first at the global warming potential in kilograms of CO2 equivalent. So of course, the Schaffner turbine is always 1 order of magnitude higher than the Piggott turbine, because it's also 1 magnitude of rated power higher. So we have, yeah, for example, 2,700 kilograms of CO2 equivalent produced in an expected lifetime of 20 years. And so what we get is 62 grams of CO2 equivalent per kilowatt hour. And the first thing that surprised us that global warming potential of the Piggott turbine is actually 50% higher than that of the Schaffner turbine. And considering that the Piggott turbine is has very low transport distances, has quite a lot of wooden parts and so on. This was really surprising for us, but the annual production was just so low that this is a driver for the CO2 per kilowatt hour. We have to say here, if we had it at a similar site like the Schaffner, it would probably lead to similar results. Yeah, and what we also see here on the right is that for both systems, about 1/3 of the emissions or the global warming potential stems from the turbine. About half of the emissions from tower and foundation, and a rather small rest goes to the electrical system. Although we have, if we look at other parameters, the electrical system, of course, is of more importance because you have more rare earth materials and so on in there. What does this mean compared to other energy sources? If we look at the Austrian grid, we have the Austrian electricity mix is around 260 grams per kilowatt hour. So even for the bigger turbine, we're quite below that. But of course, if we compare to other technologies like onshore wind, which is between 8 and 35 grams per kilowatt hour, or hydropower, I mean, that has much larger range. This really isn't great. There's much improvement potential there. For now, of course, each and every of these turbines would contribute to lower the total mix. But on the long term, this is just not good enough. So, yeah. If we look at energy payback time, that's quite okay, with 5 and 10 years respectively. So that's more or less acceptable. Could also be better, but the 5-year is also for other energy systems, this would be acceptable. Yeah, and now if we look at our improvement assessment, we see that as I mentioned, the tower has the highest contribution to the global warming potential and also to the energy demand. In both cases, we have steel towers. And so, of course, the logical thing is first to have a look, how is the impact of the primary steel which is used. So we adjusted the calculations and had a look what happens if we only use recycled steel. So this is a very, let's say, low-key measure, which is entirely realistic because it's something you can do quite easily, in fact. And here we have the impact on all categories for the Schaffner turbine, and we see here that all categories, of course, have a reduction, about 1/3 reduction for the global warming potential, quite large impact on resource use, of course. and the only thing increasing is the human toxicity, and this is because of the recycling process, which has some potentially carcinogenic emissions. Yeah, so that's the rather easy solution here. Now we can also use, so to have a look into detail here on the contribution of steel to the overall global warming potential. It's actually mostly the tower, and then we have a bit in the generator, of course, and a bit in the nacelle for the Piggott turbine here. Sorry, this is the Piggott turbine. But yeah, overall, if we take all the subsystems together, steel has a 60% contribution to the global warming potential. And this can be approximately halved if we use only secondary steel. So, conclusions from this, at sites with sufficient wind conditions, at least those wind turbines we looked at are quite able to meet their goal of low carbon production. The emissions are lower than that of the Austrian grid, but nonetheless, energy payback times and global warming potential are both higher than for other comparable renewables, even at good sites. So there's a lot of improvement which can and should be done. And the first point where this can be done is the tower, and of course the foundation. If we think, of course, of the Innoventum systems, this is basically the main idea of how it can be done. Replace concrete foundations with less consuming and potentially easily recyclable foundation systems. Replace the steel or concrete towers with wooden towers where possible, of course. So yeah, and of course, where it's possible, use secondary materials. Yeah, as I said, if concrete foundations are used, they contribute greatly to the overall emissions as well. And use of wooden towers is a very interesting alternative, but what has to be taken into the analysis here, for wood, the transport contributes significantly. So if you use local wood resources, you have very good very good results. If you have long transport ways, this decreases a lot. And of course, apart from the global warming potential, we also always have to look into the other categories. And in the case of wood, we have the preservation treatment, which can result in quite high emissions of microplastic or toxic materials. So again, this is extremely depending on where you use it, how you treat it, and so on. So it's, as always, it's difficult. And of course, for wood, recycling or reuse is not realistic. But then again, your impact is small in the beginning, so that's not so much of a problem. Okay, and that's it already. Thank you for your attention.
Yeah, thanks a lot it's indeed quite an important issue also to consider the environmental impact. And we have had some presentations in the last conference in which they looked at also at having new solutions with wood, with laminated wood. We have invited also a speaker for this year when they are doing the blades in a new material. But hopefully it will be at the next conference. They couldn't come this time. Anyway, is there any question from the audience? Apparently, you have been clear enough. And I guess if there is some question, they will just put it in the chat. But thank you for now.
Okay, thank you.